Hello and welcome in this new video. In previous video, we have seen the part A of internal first of data science. In this video, we will see the part B of the data science first internal. Let's get started. From the first question is fifth question. The solutions of this is similarities and dissimilarities in feedback. So the five question says computing dissimilarities between student feedback profile. Question briefly outline how to compute dissimilarities between students' feedback profile described by A. Nominal attributes, B. Symmetric binary attributes, C. Numeric attributes, and D. Term frequency vectors. Solution of this. First off, A. Nominal attributes. For nominal attributes, dissimilarities can be computed using the simple matching coefficient or the complementary approach. The formula of this is D equals to P minus M upon P, where P is the total number of attributes and the M is the number of matches agreements. Alternatively, use Jacquard distance for better interpretation. So equals to 1 minus number of matches upon total attributes. If students department and if a elective chosen matches in one out of two attributes, the similar dissimilarities is 1 upon 1 minus 1 upon 2 equals to 0.5. B. Asymmetric binary attributes. For asymmetric binary attributes, whereas yes is more significant than no, use the Jacquard coefficient. D asymmetric equals to D upon A plus B plus D, where is the A denoted number of attributes where profile 1 has yes and profile 2 has no, and B denoted number of attributes where profile has no and profile has 2 yes, and D number of attributes where both have no. One, two. The matching is yes yes case are including from the dominator to emphasize their significance. Numeric attributes for numeric attributes like CGPA and attendance use LU distance and Manhattan distance or Manilovsky distance. The choice depends on the distribution and domain knowledge. The formula is Manhattan and Elucidine. For heterogeneous datasets, normalize numeric attributes to 0, 1 range before computing dissimilarities. Move on to the D section. Term frequency vectors. For open text feedback, represented as text frequency vector, use cosine distance or cosine similarities to convert the distance. The formula is in there. Where x, y are the terms frequency vectors. Alternatively, elucidines distance on normalization TF vectors and TF IDFs vector for better result. Go on to the question. Sixth, distance computation. Question says that suppose two student faculty interaction profile are represented as a tuple. The tuple is 22, 1, 42, 10 and second one is 20, 0, 36, 8 where attributes represent or spent in mentoring project, review attended assignments, submitting in infrastructures, users count. Compute a Euclidean distance, Manhattan distance, Minkowski distance, and supremum distance. Solution: let P1 equals to 22, 1, 42, 10 and P2 equals to 20, 0, 36, 8. Euclidean distance equals to getting this formula. Applying this formula to get the answer of 6.708. By Manhattan formula, you can see carefully taxi cab distance equals to 11. The answer is 11 of this question. And the C section is Minkowski distance with h equals to 3. Applying the formula in this. equals to the answer of this method is 6.155. Last question of this question D. Supreme distance is 6. Let's move on to the seventh question. Median approximation for large feedback data sets. The median score is often as a key holistic indicators of faculties or infrastructure performance when dealing with the massive student feedback database sets. Propose method for median approximation. Analysis their complexity and suggest hierarchical to balance the accuracy versus efficiency. The solution of this question is context and motivation. In massive data sets with millions of feedback regarding and recorded, compute the exact median is computationally expensive 0 on n log n. For sorting, we need to efficiently approximation that maintain reasonable accuracy while reducing computation time. Proposed median approximation method. Method 1. Sampling based approximation. Approach: draw a random sample of size k from the dataset. Compute the median of the sample and use it approximation of the population median. Complexity O k log k, where k is less than the n. Accuracy trade-off: large sample size, high accuracy and high cost. And smaller sample size is low accuracy but fast computation. Heuristic: use k is under root n over k, which is 10,000, which is a smaller or balanced result. Confidence interval for large sample. The sample median covers to normal distribution. Confidence intervals can be computed using bootstrap method. And second method is quantile sketch algorithm, T-digest KLL. Approach: use streaming quality screens that maintain approximate quantile information without storing old data points. Complexity is 0 n from insertion and 0 log m or log m from median query, where m is size typically is smaller than n. Accuracy high, typically within 1% of true median. Advantage: handle streaming data efficiently. Second, low memory footprint, constant space. And third one is parallelize across data partition. Implementation of this is library like Apache Data HS provide ready to use implementation. The third meta is partition based approximation, quick select style. Approach: use randomization selection algorithm to find the median without full sorting. Expected complexity is O(n), but worst case complexity is O(n) n square. Heuristically, to balance accuracy, use iterative refinement. First, partition around a random pivot, and second, if median not yet located, recursively partition the relevant half. Third one is use early termination when sufficient accuracy is achieved. Fourth one is histograph based approximation. Build a histograph for feedback score, then compute the median from the histograph bind. Complexity O n plus b, where b is the number of binds. Accuracy depends on bean current, and finer bind yield better accuracy. Hierarchy: use b equals to min 1000 comma under root n. Binds for good balance. Comparative complexity analysis, see in this table. Comparison of median approximate method. Recommended approach of student feedback for massive feedback and datasets. We recommended a hybrid strategy. First one is online phase. It used the TIS on KLN sketch to maintain the streaming median estimate as feedback achieve the complexity of ON time and constant space. Second one is predictive verification. Every 10,000 records validate sketch accuracy using quick select on a sample subset. Third one is final reporting output digest and median as a primary estimate and confidence interval point. And this achieve the O and time complexity time with the near exact accuracy of 98% plus while maintaining streaming capacity. And move on to the next question. Question number 8. Student faculty similarities analysis. Question says that consider student faculty similarities analysis a sample data sets of two attributes faculty's responsiveness and infrastructure support is provided in a student table. Given a feedback query x equals to 1.4, 1.6, okay, A rank existing student feedback profile by similarities using Euclidean and Manhattan in superum and Gaussian similarities. B. Normalize each student vector to unit length and recompute using residence distance. Part 1 Computing Similarities and Ranking. We have the 5 student profile, tuple 4 of faculty responsiveness and infrastructure support. S1 is equals to 1.5 upon 2 and S2 equals to 2 comma 1.9. S3 equals to 1.6 comma 1.8 and S4 equals to 1.2 comma 1.5 and last one is S5 equals to 1.5 comma 1.0. Query vectors x equals to 1.4 comma 1.6 s on applying LUCD in distance. So we have the result of different type of methods equals to the approximate values. There are S1 is 0.412 and S2 is 0.671 and S3 is 0.283 and S4 0.224, S5 is 0.608. So, elucidating ranking is smaller distance equals to most similarities. So, find the most similarities in this. S4 Manhattan distance says that Manhattan distance x comma 1 si equals to in module x1 minus si1 plus module x square plus not this plus is minus 8 I2. So the answer of S1 is 0.5, S2 is 0.9, S3 is 0.4 and S4 is 0.3 and last one is S5 equals to 0.7. So the Manhattan ranking is S4 0.3 is minimum, S3 greater than S1. S3 is minimum S1 and S1 is minimum of S5 and S5 is smaller than S2. Supreme distance method. Supreme distance method. On applying this formula, d x comma s1 by maximum. So the s1 is 0.4, s2 is 0.6, s3 is 0.2, and s4 is 0.2, and s5 last one is 0.6. So the answer of this is similar. This S3 is equals to the approximation of S4 and those values are greater than S1, S5 is greater than 2 and S1 is greater and S2 is greater than S1. similarities and cosine distance. On applying this formula, we have the answer of x equals to approximately 2.126, and S1 is 215, 2.5, and S2 is 2.759, and S3 is 2.408, and S4 is 1.921, and last one S5 is 1.803. Dot product of this S1, the dot product of x and S1 equals to 5.3, and S2 5.84, and S3 5.12, and S4 4.08, and S5 is 3.7. Cosine similarities of seen it there. The cosine ranking of this is X S3 is similar as S4, and S5 is greater than S2, and S2 is greater than S1, and S1 is greater than S3 and S4. And summary table set providing the ranking in the first ranking is Euclidean in S4, rank 1, rank 2 is S2, S3, and rank 3 is S1, and the rank 4 and 5 is S5 and S2. According to this table, you can see there ranking comparison across distance. Second one is B, normalization. You see dense distance normalize each student vector to unit length. Unit length. Normal vector position S1 equals to 0.6 comma 0.8, and S2 equals to 0.725 comma 0.689, and S3 equals to 0.664 comma 0.747, and S4 equals to 0.625 comma 0.781, and S5 equals to 0.832 comma 0.555. Computing illusion distance normalized vectors. So the normalized Eliciting ranking equals to S3 is greater than S4, and S4 is greater than S1, and S2 is smaller than S1, and S2 is greater than S5. You see in the normalization ranking. So thank you.